Dear students, in the previous lecture we discussed about the nature of charges and their properties in detail. In this lecture we will learn about the force exists between the charges, the Coulomb's law of electrostatics. Lecture number 2 will be divided into 3 parts. In today's lecture we will learn about Coulomb's law of electrostatics, and in the next part we will discuss some important points of Coulomb's law and some numerical examples. Let us set up some convention. The total charge on the particle will be represented by small letter q or capital letter Q. As we know that like charges repel each other and unlike charges attract each other, so to graphically represent such a scenario, always draw the tail of force vector on the particle along the line joining the two particles. For example, consider two positively charged particles Q1 and Q2. Separated by small distance. As the charges are identical, the force will be repulsive. If we focus on Q2, the force will be drawn by putting the tail of vector F on Q2 pointing outwards. And for the force acting on Q1 will be drawn by placing the tail of vector F on Q1 pointing outwards. Now if both Q1 and Q2 are negatively charged, the force will again be repulsive. The scenario will be same as discussed for positively charged particles. And if one of the charges Q1 or Q2 is negative, the force will be repulsive and be drawn in the same fashion by putting the tail of the force on the charges, but this time pointed inward. Vectorially, the electrostatic force can be described in terms of unit vector R along the axis through the two particles radially away from the reference particle. Consider two positively charged particles, that is Q1 and Q2, separated by small distance. If we consider Q1 as the reference charged particle, then our unit vector will be radially away from Q1 like this. Magnitude of the charged particles is represented by modulus. Where Q represent either positive or negative charge. As electrostatic force is mutually interactive, then the force exerted on charge Q2 by charge Q1 is represented by F21 and can be read as force on 2 by 1. Similarly, the force exerted on charged particle Q1 by charged particle Q2 is represented by F1, 2 and is read as force on charged particle 1 by charged particle 2. Let us discuss Coulomb's law of electrostatics. This law states that the magnitude of force of attraction or repulsion between two stationary point charges is directly proportional to the product of the magnitude of two charges and inversely proportional to the square of distance between them. Mathematically, the above statement can be represented as: consider two positively charged particles Q1 and Q2 separated by distance r, then the magnitude of force will be directly proportional to the product of the magnitude of the two charges, that is Q1 mod into Q2 mod. This is equation number 1. And this force is inversely proportional to the square of distance between the two charged particles. This is equation number 2. Combining equation 1 and equation 2, we can write F is proportional to Q1 mod into Q2 mod divided by R squared. To remove the sign of proportionality, we put a constant K Q1 mod Q2 mod divided by R squared. This is equation number 3. Equation 3 gives us Coulomb's law of electrostatics, representing the magnitude of electrostatic force, where K is known as electrostatic constant or Coulomb constant is electrostatic constant. Historically, K is given by 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of vacuum or air. Epsilon naught is in empirical proportionality constant. Its numerical value turns out to be 8.85 into 10 raised to power minus 12 Coulomb square per Newton meter square. The unit of epsilon naught can be easily determined from equation number 3. Let us write equation number 3 as F is equal to 1 by 4 pi epsilon naught Q1 mod into Q2 mod by R squared. So from here epsilon naught can be written as 1 over 4 pi Q1 mod Q2 mod divided by F into R squared, and if we plug in the units of Q1, Q2, F and R square, so it turns out to be Coulomb square per Newton meter square. So this is the unit of permittivity of Faiq or air. Let us define permittivity of a medium. It is the conducting ability of the medium to allow electric lines of force through itself. Or we can also express permittivity as how much a medium is polarized in the presence of a charge. On the other hand, the electrostatic constant depends upon unit system For example, in SI units, electrostatic constant can be written as 1 by 4 pi epsilon naught, putting the numerical values of pi, that is 3.14, and epsilon naught, that is 8.85 into 10 raised to power minus 12 Coulomb square per Newton meter square. So the numerical value of electrostatic constant will come out to be 8.99 into 10 raised to power 9 Newton meter square per Coulomb square, which is close to 9 into 10 raised to power 9 Newton meter square per Coulomb square. In CGS units, epsilon naught is equal to 1 by 4 pi So electrostatic constant K can be written as 1 by 4 pi epsilon naught. Plug in the value of epsilon naught, this equation, that is 1 by 4 pi. We will get, that will cancel out 1 by 4 pi, and we will get 1. So in CGS units, the value of electrostatic constant is 1, while in SI units, the numerical value of electrostatic constant is about 9 into 10 raised to power 9 Newton meter square per Coulomb square. On the other hand, the electrostatic constant K depends upon in which medium the charges are placed. So if the space between the charges is filled with non-conducting medium or an insulator called dielectric, that is Q1 and Q2. Now this space between the two charges is filled with some dielectric, with dielectric constant capital K or relative permittivity epsilon r. Then the relative permittivity of this medium is defined as the ratio of permittivity of a medium, permittivity of vacuum. This implies that epsilon is equal to epsilon naught into epsilon r. Then the electrostatic constant can be written as, in the presence of medium, as K prime is equal to 1 over 4 pi epsilon. Now plugging the value of epsilon in this relation, we will get 1 by 4 pi epsilon naught into epsilon r. Separate 1 over epsilon r from the 1 over 4 pi epsilon naught. So we can write the above equation as, now the term in the parentheses is the electrostatic constant when there is vacuum between the charges. So we can write K prime is 1 over epsilon r into K. This is equation number 4. Now we can express Coulomb's law of electrostatic in the presence of dielectric medium. The force in the presence of medium will be equal to K prime Now we can express Coulomb's law of electrostatic in the presence of dielectric medium. F medium will be equal to electrostatic constant K prime in the presence of medium into Q1 mod, Q2 mod by R squared. We can write this equation as K by epsilon r Q1 mod into Q2 mod by R squared, where K prime from equation number 4 is replaced by K by epsilon R. Now, the above expression can be rewrite as 1 over epsilon R K Q1 mod into Q2 mod by R square. Recall equation number 3. The terms here in the present Recall equation number 3. The term in the parentheses is the force when the charges are placed in vacuum. So we can write F medium is equal to F by epsilon R. This is equation number 5. As we know that for all dielectrics, epsilon R is greater than 1. So from equation 5 we can write F medium will be always less than F. And this can be easily understood from equation number 5, as this denominator epsilon R is greater than 1, then F medium will be lesser than F prime. F medium and F will be equal if epsilon R is equal to 1, which is the relative permittivity of air or vacuum. Otherwise, as the epsilon R increases, the force in the presence of medium between the charges will decreases. Equation 5 can also be written as epsilon R is equal to F divided by F medium. So one can also define the relative permittivity or dielectric constant as the ratio of the two forces when the charges are placed in air to the force when there are some non-conducting medium between the charges. Let us now express Coulomb's law of electrostatic in vectorial form. Consider two positive charges Q1 and Q2 separated by distance r. Now to find the force exerted onto by charge particle 1 will be equal to the magnitude of force. So the magnitude of force will be 1 by 4 pi epsilon naught Q1 Q2 by R squared. And the direction of this force will be radially away from Q1. As we stated the convention, we will put the tail of F21 on Q2 as we consider Q1 as a reference charge particle. So R unit vector will be radially away from Q1. So the direction of F21 will be r unit vector. This is equation number 6. Similarly, we can find the force exerted on 1 by 2 as, again the magnitude of this force will be 1 by 4 pi epsilon naught. We can shuffle the position of charges, that is force exerted on Q1 by Q2 over r squared. And the tail of F12 will be placed on Q1, but this time the direction of F12 will be opposite to that r unit vector, that is like this, which is minus r unit vector. So we can write the direction of F12 as a minus r unit vector. Simplifying the above expression, we can write minus 1 by 4 pi epsilon naught Q1 Q2 by r squared r unit vector. This is equation number 7. Now we can plug in equation 6 in equation 7 to get F12 is equal to minus F21. This expression tells us that Coulomb's law of electrostatic obey Newton's third law of motion. The electrostatic force is mutually interactive. The magnitude of force will be same, but direction of the force will be opposite. Now more generally, the Coulomb's law of electrostatic in vectorial form can be written as F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by r squared r unit vector. So this is the general vectorial form of Coulomb's law of electrostatics. So we can determine the magnitude of force by using the relation 1 by 4 pi epsilon naught Q1 Q2 over r square, and the direction of the force will be determined by r unit vector, where it should be noted that r unit vector magnitude, that is equal to 1 and is given by r vector by r magnitude. So this represents the position vector, which can be in 3 dimensions written as a I hat plus b j hat plus c k hat, and its magnitude can be written as a squared plus b squared plus c squared under the square root. Unit of electric charge. The electric charge is said to be 1 coulomb if two identical charges are placed 1 meter apart and they exert a force of 9 into 10 raised to power 9 Newton on each other. Let us do it mathematically. For example, we have two identical charges Q1, Q2, that is equal to Q, and the charges are 1 meter apart from each other, and they exert a force of 9.0 into 10 raised to power 9 Newton on each other. Then what will be the magnitude of charge? We know that electrostatic constant is also equal to 9 into 10 raised to power 9 Newton meter square per Coulomb square. Now from Coulomb's law of electrostatic, F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R squared, where 1 by 4 pi epsilon naught is equal to K. Charges are identical, so Q1 Q2 product will be Q squared divided by R squared. Now we can write this expression as Q squared is equal to F R squared by K. Plugging the numerical values, that is 9.0 into 10 raised to power 9 Newton is the force when the charges are 1 meter apart, and the dielectric constant is 9.0 into 10 raised to power 9 Newton meter square per Coulomb square. So the Newton will cancel out with the Newton, meter square will cancel out with the meter square, and the number 9.0 will also cancel out. So we will get Q square is equal to 1 Coulomb square, or Q will be equal to plus minus 1 Coulomb. So the charge is said to be 1 Coulomb if two identical charges exert this much force when they are 1 meter apart. So it is a huge amount of charge. We can write also the submultiple unit of electric charge, that is microcoulomb is equal to 10 raised to power minus 6 Coulomb, millicoulomb that is 10 raised to power minus 3 Coulomb, and so on.